On to adiabatic processes. Now, we stopped or didn't do adiabatic processes until the very end, because an adiabatic process is one where the heat going in or out of the system is zero. So when we look at our first law of thermodynamics, delta U is equal to Q minus W. For an adiabatic process, Q's gone, okay? This is zero. So when we write this, delta U, the internal energy, is just equal and opposite to the work that's done by the gas, okay? So what does that mean? What does that mean for the adiabatic process? Well, that's very important, because if we are undergoing an expansion where work is positive, that means delta U has to be negative. Remember, work is opposite of the change in internal energy. So for an adiabatic gas, or I'm sorry, for an adiabatic process, for a gas undergoing expansion, okay, a drop in the internal energy means that it's getting colder. Okay, it's cooling off. If we compress an adiabatic gas, compression, where work is negative, that means that the change in internal energy must be positive. Well, what's happening to the gas in that case? The gas is getting hot because the internal energy is going up, and internal energy is a function of the temperature. So this is a really interesting thing that we see. If we don't allow heat to enter or leave a gas, if we allow it to expand, it's going to cool off. If we compress it, we can heat it up. And this has all kinds of really neat implications, okay? In terms of expansion, we actually use adiabatic expansion to cool gases off and liquefy them, okay? Did you ever wonder where liquid nitrogen comes from? We keep compressing the gas to higher and higher pressures, and at the same time, we take energy out of the system. And then we rapidly allow it to expand, and as it does so, the rapid expansion causes it to get very, very cold. And if we do this repeatedly enough times, we can get the gas cold enough that the nitrogen will liquefy. Okay? On the other hand, we can use rapid compression to actually heat things up. Okay? Trying to think of some good examples here. Obviously, if you inflate a tire, it's going to get warmer. But in fact, in laser fusion, when they rapidly compress a target, and they usually do it with X-rays or laser, they can increase the temperature up to a point where nuclear fusion will take place. And this super compression, we call it inertial confinement, the process of compressing it and not allowing the energy to escape, is thought to be one way that we might be able to get energy out of nuclear fusion. So very, very important process here. For our purposes, think about any time we do an adiabatic expansion where we don't allow the heat to keep the gas warm, we're not heating the gas, it's going to get cold. Adiabatic compression, the gas is going to get very hot. Okay, again, for adiabatic processes, Q is going to be equal to 0 by the first law. Delta U is equal to, that should be negative, okay? The change in internal energy is going to be equal and opposite to the work done. For adiabatic processes, and this is not written so well, so I'm going to rewrite it right here. P times V, it's only V, raised to the gamma power is going to be a fixed number. It's going to be a constant. Okay? Now, gamma represents the molar heat capacity at constant pressure divided by the molar heat capacity at constant volume. It's called the adiabatic index. And we remember CP for a monatomic gas was 5/2 R. CV was 3/2 R. So for a monatomic ideal gas, 5/2 R divided by 3/2 R gives me 5/3. Okay. For a diatomic gas, it was 7/2 over 5/2. So it would be 7/5. And as the gases become more and more complicated, generally gamma begins to approach 1. But again, this is known as the adiabatic index of the gas. And as long as P times V raised to the gamma power is constant, you're undergoing an adiabatic process. Okay? So again, no heat flows in or out of the system. Delta U is equal to the equal and opposite to, delta U is equal and opposite to W. We can imagine demonstrating this right here if we had this little piston and we had some gas contained within here right there, and we allowed the piston to move, it would raise this weight, right? The work done would be equal to the change in gravitational potential energy of that little mass. Okay? Where'd that energy come from? It came at an expense of the internal energy. This gas is cooling off because it's doing work on the outside environment. And again, here is showing the adiabatic expansion of an ideal gas. We start at this point right here, and we expand to some point here. All right. Let's take a look at this, because I do want to show you that, in fact, that we're dropping our temperature and we're not following an isotherm. Okay. For constant temperature, we know PV equals nRT. If the temperature is constant, then the pressure would change inversely with the volume. So for instance, if we went from 1.5 meters cubed up to 3 meters cubed, we're doubling this right here, then the pressure should be 1/2, should be down right there. So my isotherm, my isotherm is actually following this curve right here. Okay, we can clearly see that this adiabat is much steeper than that. It drops off faster than 1 over V. Okay. All right. We sort of did some of this derivation previously, but this is, again, is showing that, in fact, this has to remain a constant. Okay, I'm not going to go through that, but again, that's related to the specific heat capacity, the molar heat capacities. And more practically, drawing isotherms and adiabats on the same curve, on the same PV diagram, you can clearly see that the adiabat decreases faster than the isotherms. They're pretty close, okay? But again, remember, we're losing temperature during this expansion, all right? And if we allow the gas to expand, we go this way, it's going to cool down. So right here, we're at 700 degrees Kelvin. Right here, we're at 1300 degrees Kelvin. So let's actually start from there. Here we can actually prove this. We follow this adiabat. we're at 1300 degrees Kelvin right here. If we expand from here to here, the gas is going to cool. It's going to drop nearly by 1/2 its initial temperature. Likewise, if we went the other way, if we went with a compression, we compress it from here to here, it's going to jump from 700 degrees Kelvin to 1300 degrees Kelvin. So an isotherm for a gas is a contour on the PV diagram where the gas would be kept at constant temperature. An adiabat would be a curve where the heat exchange with the outside would be 0. No heat would go in or out, and it would decrease in temperature if it expanded. It would increase in temperature if it were compressed. It's really difficult to figure out the area underneath an adiabat. We weren't able to do it with our isotherm, but under an adiabat, I'll be honest with you, I sort of just copied this. This is really beyond even my ability to do calculus. I would have to really sit down and play with different substitutions here. But basically, you can come up with an analytical solution to the work being done. But, that's not really important for what we're doing here. So let's look at some practical applications of adiabatic processes. Here we have, on a nice summer day, sunlight's hitting the ground, it's heating up the air is getting warm, and it gets hot, and it also gets humid, okay? What is going to happen to that air? Well, at 92 degrees Fahrenheit, it is going to experience buoyancy, and it's going to rise and begin to expand. Well, remember, Q is equal to 0. So what this means is thermal energy cannot come in or out of the system. So if it's expanding, the temperature is going down. So let's say that little piece of air is now rising into the atmosphere. And at 3,000 feet, the pressure is lower, so it's going to occupy more volume. And it's dropped from 92 degrees Fahrenheit to now a more reasonable 76 degrees Fahrenheit. Okay, now it's up at 6,000 feet, and the temperature's dropped more. Now it's down to 60 degrees Fahrenheit. Now, what's interesting here is the dew point has remained constant. It still has the same amount of water content that it had when it was on the ground. We haven't lost any mass here. What's happened is it simply started rising higher into the atmosphere and getting colder and colder. Well, that's why you get these big puffy clouds on a warm summer day. At the surface, we're generating these little convective cells. And these little convective pockets, as they rise into the atmosphere, get colder and colder. Eventually, when they get cold enough, the temperature drops below their dew point. The dew point is the temperature at which the air can no longer hold the moisture. So what happens? You get condensation. A cloud is your condensation. So these little cumulus clouds that appear, look like little balls of cotton, are the result of this adiabatic expansion that happens again on a warm summer day. It's a little blob of warm, moist air rising into the atmosphere and forming a cloud. Of course, cloud formation can be more complicated and more violent than just a little bit of a puffy cloud. Now, again, it's also triggered by warm and cold interfaces. So the complexity of what we're going over here doesn't reach the complexity of what actually happens in nature. But again, you can imagine this warm, moist air at the surface going higher and higher and carrying with it water vapor. Okay? So two things are going to happen here. One, the adiabatic process, the adiabatic expansion is going to cool it off and cause this water vapor to form clouds, water droplets, even ice crystals. But it's also carried all this moisture up with it. So what's the moisture going to have to do? It's going to have to start falling back downward. Okay? And as it does so, all that gravitational potential energy that it has at the top of the cloud is now converted into kinetic energy as it comes back down in the form of rain. Okay? Well, this also produces strong downdrafts. Okay? The water, the ice heading for the ground, heads downward at a pretty good velocity. It displaces the air in front of it, causing even more air to get pushed up into the atmosphere. More latent heat is released as the warm, moist air, this is usually the warm air in front, is converted from a vapor to a liquid. And then behind here, you've got the cold air, okay, which is allowing even more of the moisture to condense. So what's interesting is these clouds or these storm systems can actually act like heat engines, where the source of the heat, okay, our hot reservoir, can be the warm, moist air in front of a cold front, and where we dump the energy, behind it is the cold air mass, okay, on the trailing edge. Again, I'm oversimplifying a much more complicated process. But again, we can understand how the air, as it expands, is going to cool off. It's going to condense. It's going to turn into moisture. That moisture is going to fall and release the energy that it took to the top of the cloud with it. In California, they have a very interesting but also dangerous weather phenomena called the Santa Ana winds, which is actually sort of the reverse of the storm cloud that we just showed. And the Santa Ana winds basically blow from the inlands at higher altitude to lower altitudes near the coast. So what happens here is you have on the mountaintops this colder, drier air. Okay. Obviously, the fact that it's cold means that it can't carry as much moisture with it. And this cold, dry air will now flow down the mountainside. And as it does so, it compresses. And two things are happening here. One, it compresses due to the lower altitude. You're just simply at a higher pressure near the coast than you are on the mountaintops. But also, it is forced to occupy a much smaller airstream, so it's going to accelerate. And of course, this is really not such a great thing for wildfires, because coming from the mountaintops, they're really carrying very little water moisture with them. Now, the air not only is very dry, it's very hot, and it can create tremendous wildfire problems in these areas. So there's your opposite effect right there. Warm, moist air rising to the upper part of the atmosphere, adiabatic expansion, it cools. Santa Ana winds, the air coming down from the mountains is compressed, becoming very, very hot. Practical applications for this, if you spray an aerosol can long enough, you'll notice that it gets quite cold. And that's because we have a liquefied gas inside here, some sort of liquefied propellant, which undergoes a phase change. We know that liquids are approximately 1,000 times more dense than gases. If we allow this to expand, this adiabatic expansion rapidly cools the gas inside it. In fact, probably more practical application would be an air conditioner, where the liquid refrigerant is allowed to go through a small nozzle. And as it does so, the adiabatic expansion causes the refrigerant to go from a higher temperature to a much lower temperature. And that's how we basically use the refrigerant to pick up the heat from inside a refrigerator, inside a freezer, right? We allow it to expand, it drops in temperature, it'll absorb heat. Then we put it through a compressor, we'll heat up and dump it out, or dump the heat out. The refrigerant stays in there, hopefully, using a heat exchanger. Of course, if you fill a tire up with air, you'll notice that both the tire and the nozzle from the air compressor heat up. And this is because, again, you're doing work on the gas. The heat is able to escape in the form of a higher temperature. So let's summarize. Looking at the different thermodynamic processes, in terms of calculating work, isobaric's really easy. It's just pressure times the change in volume. Got to do a little edit right there. Isochoric, there's no volume change, so no work is done. Isothermal, that's where we have our natural log, okay? And of course, for adiabatic, where Q equals 0, we can say that the work being done is equal and opposite to the change in internal energy, okay? In terms of Q, all right, for an isobaric process, we can use the fact that Q is equal to N Cp delta T. Notice we're using the molar heat capacity at constant pressure. Adiabatic involves no heat exchange, so that's 0. Isochoric, no work is being done, so Q just represents the change in internal energy. And for the case of isothermal, okay, there's no change in internal energy, so both the work and the Q are the same, okay? Actually, if we look at this, the work that's being done outside, okay, the work that's being done to the outside environment is coming from the heat, which is being input right there, okay? And again, in each case, there's a change in internal energy as long as there's a change in temperature. That would be true for isobaric. Adiabatic, there's no heat added or taken away, but certainly there's a temperature change. Isochoric, the pressure changes as a function of the change in temperature, and only isothermal has no temperature change. Okay? But again, you know, if we're going to focus on anything from this chart, this work done, that's the important one. All right?